Okay, so today I just wanted to go a little deeper into proving for you why we have these certain relationships for angles and arcs. So the first one that I'm going to go more in depth on is what happens when we have a vertex inside of the circle. We've already told you that the relationship is that the angle here, x, is going to be the average of these two intercepted arcs. So 1/2 the sum. So I want to kind of prove to you why that's true. So before I go too deep, let me just remind you of a relationship that we saw last semester. So here's a triangle. We proved why it is already that the interior angles sum to 180. And then we talked about that exterior angle right here, angle 4. And we proved that this angle, this exterior angle, is the same as the sum of the two remote interior angles, right? Because we know that these add to 180. We know that these add to 180. They form a linear pair. So we can connect the sum of 1 and 2, those measures, being equal to the measure of 4, right? Measure of 1 plus measure of 2 equals measure of 4, right? That was the exterior angle theorem. We proved that last semester. So keep that in mind as I build out my explanation. All right, so looking at my diagram, I'm going to have you extend right here. Make a segment that extends from this point to this point right here. And I'm going to have you label this angle here as 1 and this angle here as 2. Okay, so what I've essentially done is I've made x an exterior angle. 1 and 2 are the remote interior angles. If I sketch that out to the side, kind of looks like this right now, where that's 1 and 2, that's where x is. So again, I have an exterior angle, and I have these two remote interior angles. So I know that x is equal to the measure of 1 plus the measure of 2. An exterior angle is equal to the sum of the two remote interior angles. Now, if I look at where angle 1 is right here, this angle right here, okay, I know that its vertex is on the circle. So I know that this angle right here is going to be half of this intercepted arc that I've defined as z. So it's going to be 1/2 whatever z's measure is. And if I go over to where measure 2, where angle 2 is here, its measure will be half of its intercepted arc, right? Because its vertex right there on the circle. So half of y. Oops, wrote that goofy. Half of y. Okay, so now I can use a little substitution. I can say that x is equal to half of z plus half of y. Okay, and then once I'm here, I could divide out the 1/2. I can treat it like it's a GCF. So half of z plus y, or y plus z. I'll put it as y plus z because that's how I wrote it up above, right? But the order really doesn't matter. All right, so we've written a proof, right? A little mini proof off to the side that shows why it is that this angle vertex inside of the circle has a measure that is the average of the two intercepted arcs. Okay, next one I want to prove to you is this one. So how about when the vertex is outside of the circle, right? I've already told you that right here, if this vertex is outside of the circle, this angle is half the difference between the two intercepted arcs here and here. All right, so first thing that I want you to do is I want to add a segment. Right, a lot of what we do, we prove using triangles. So let's connect here to here and let's make a triangle. So now I have these 3 interior angles would have to all add up to 180. We know that. I'm going to call this angle right here angle 1 and this angle here angle 2 for just a moment and build my equation that says that x plus the measure of angle 1 plus the measure of angle 2 has to sum to 180. right? We know that the interior angles of any triangle have to add up to 180. All right, so now if I look at where, let's say that I start by looking at where angle 1 is. This angle right here that's right beside it, right, here's the vertex on the circle. It has to have a measure that's half of its arc. And this arc right here is y. So this would be half of y. So now if I go over to where angle 1 is, right there, I know that these two angles form a linear pair. They have to be supplements. So angle 1 would have to be 180 minus half of y. Right? It's the supplement of the angle that's right beside it. Okay, if I look at where this angle is, where I've called it angle 2, put a little arrow there, I see that here the vertex is on the circle. This angle that I have as angle 2 would have to be half of z. Half of z. Right? I usually just cross it so it doesn't look like a 2. So now I've defined all of these angles now as variables, and I'm gonna substitute in for the measure of angle 1, the 180 minus half of y, and in for the measure of 2, half of z. Okay, now I'm just going to rewrite that substituted in. So x plus 180 minus half of y plus half of z equals 180. So if I subtract 180 from the left, it's going to subtract from the right as well. So I can go ahead and cross those away. So now I have, let me clean it up, I have x minus half of y plus half of z is equal to 0, right? That's where I'm at right now. But I want to get the angle. I want to get angle x right here. I want that all by itself. So I'm going to add half of y to the other side and subtract half of z to the other side as well. So now x is by itself, right? X equals half of y minus half of z. And now if I factor out, divide out my GCF of 1/2, I'm leaving behind that y minus z, right? So x, this angle, is going to be half the difference between the big arc, the big intercepted arc, and that small intercepted arc right here. Okay, one more relationship. So here I'm really giving you the same thing, right? The vertex is outside of the circle right here, and I have these two intercepted arcs. So honestly, I could use the same formula that I just showed you. So I could use that formula above, or I can see that this is really a special case because I have two tangents this time. Right, two tangents because I see that this line makes contact in one spot, this line makes contact in one spot, tangent segment, tangent segment. So yes, that formula above right here, this relationship holds. I can do 1/2 the difference between the intercepted arcs, but I can also see this, right? If I connect those 2 points of tangency like so, let's say I label this as angle 1 and this is angle 2. Okay, first thing that I see now that I have that labeled, I know that x plus the measure of angle 1 plus the measure of angle 2 is going to have to add up to 180, right? Because interior angles of any triangle add to 180. But now I can see that this angle right here, vertex is on the circle. It's going to have a measure right here that's half of its intercepted arc, which is z. So half of z. And over here for angle 2, I'm going to see the same thing, right? I'm going to see that this angle right here is going to be half of its intercepted arc, also z. So half of z. Okay, and right there I can see, oh yeah, that makes sense because this is really an isosceles triangle because these two tangent segments are congruent. These two base angles, they have to be congruent too. So now if I plug in for the measure of 1 and the measure of 2, here's half of z, the other half of z. So now if I clean it up, I have x plus half of z plus half of z equals 180. X plus z, right, because half and half, if I add those, that makes 1, equals 180. Right, so I see another little shortcut that only works when I have the two tangents because, right, again, it's that isosceles triangle. So I see that x plus z right here end up adding to 180, right? And that really stems from these two base angles, both of them being half of the same intercepted arc. So this is that special case where this angle on the outside and that small minor arc, that intercepted arc, happen to be supplements. They add up to 180. So again, this is the angle, and this is the smaller arc, right? The minor arc, right? And only because we have two tangents, it's our special case. All right, that's all I have for today. Have a good day.